Integrals involving transcendental functions. Here's a list of some general antiderivatives or indefinite integrals involving transcendental functions. If I have the integral of 1 over a squared plus x squared dx, that becomes the transcendental function 1 over a arctan of x over a plus c. So it's important to know here that a is a constant. A is a constant. And if I have the integral of 1 over the square root of a squared minus x squared dx, that becomes arcsine of x over a plus c. If I now have a negative in the integrand with the same denominator, then that ends up being arccosine of x over a. And then finally, I have the integral of 1 over x times the square root of x squared minus a squared dx. That becomes 1 over a arcsecant of x over a plus c. So notice the only ones that have 1 over a in front are the ones that involve arctangent and arcsecant. Let's take a look at a few examples. We have first the integral of 2 all over 9 plus x squared dx. So here I'm going to reference my general antiderivatives that when I have 1 over a number squared plus x squared dx, that becomes a version of arctangent. Well, here I have a 2 on the top, but remember I can go ahead and take the 2 out of the integral. So now I have 1 over 3 squared plus x squared dx. So it looks exactly like my formula here with 3 in the place of a. So I can go ahead and go straight to my answer, which is going to be that 2 in the front times 1 over a being 3, and then arctangent of x over 3 plus c. So here I can make this 2/3 arctangent of x over 3 plus my constant. And we could also have chosen to write tangent inverse as opposed to arctangent. Looking over here at example B, I have the integral of 3 all over x times the square root of x squared minus 81. So now I am going to refer to this bottom general antiderivative because I can see here I have that x on the outside and the square root of x squared minus. I can rewrite 81 as 9 squared. So I'm looking at using this antiderivative involving arcsecant. So I do have this 3 on top, but again, we can think about leaving that in the front when I write my final answer here. So I'm going to leave the 3 that's out in front. And I'm going to remember that 81 is 9 squared, so I'm just going to write that off to the side. So arcsecant, just like arctangent, has 1 over a in front. So we're going to have 3 times 1 over 9 arcsecant of x over 9 plus c. So we have that x over a. The a value is 9, since 9 squared is 81. And then here I can reduce the coefficient to be 1/3 arcsecant of x over 9 plus c. So really what it comes down to with these two problems is recognizing that the integrand has one of these forms so that I can go straight to one of these transcendental functions as my answer. On this example, I have the integral of dx over the square root of 9 minus 49x squared. So here, if I take a look at my formulas, it looks a lot like the second one. So I have the dx and then the square root of something squared, so 9 is 3 squared, but instead of minus just a single variable, x squared, I have 49x squared. So what I'm going to do on this problem is I'm going to rewrite it. I'm going to think about it as, I'll leave just a 1 on top so that I can really see the formula happening. So I have a 1 over the square root of 3 squared minus the quantity 7x squared. So here I still don't have just x squared like I need to use this arcsine formula. I would need just a single variable. But what I can do is I can make a u-substitution on just this part here, 7x. So notice we wouldn't let u be the entire piece underneath the radical, because if I let u be the entire 9 minus 49x squared, the derivative of that would be negative 98x, and I don't have an x in the numerator. So here I'm just going to let my u be 7x, and then du is 7dx. Well, I just have a dx over here, so I'm going to divide by 7. 1/7 du is equal to dx. So now I'm going to come back and I'm going to make my substitution. So this is going to be equal to the integral of, well, this 1 dx becomes 1/7 du. So I'm going to keep the 1/7 in the front, and I'm going to keep a 1 on the top. I'm going to keep my du, and then the denominator is now the square root of 3 squared minus u squared. So I was able to make it just a single variable. It has to be just a single variable squared to apply this formula. So now I can go ahead and apply this formula, but remembering to keep u in the place of x, and my value of a is 3. It happens to be this nice value since 9 is a perfect square. So we're going to have the 1/7 in front, and then arcsine does not have that 1/a in front. So it's just 1/7 arcsine of u/3 plus c, so keeping the u variable, but then going back and recognizing that I need to substitute 7x back in for u in my final answer. So I get 1/7 arcsine of 7x/3 plus c as my final answer. So this one is a little bit trickier to recognize that it's going to become an arcsine, but here if you were to try u substitution first just with the whole piece underneath the square root, I wouldn't be able to have that du work out for me with the negative 98x. I don't have an x in the numerator. On this example, I want to integrate the quantity 8x plus 3 all over the quantity 1 plus 4x squared dx. Now this doesn't look like one of these integrands over here because I have a binomial on the top. So if I were to just try to start this by doing a u substitution right away, so if I let u equal the denominator, u is equal to 1 plus 4x squared, du is equal to 8x dx, it doesn't quite work out. So I see an 8x, but I have this plus 3, and I can't do this u substitution with this plus 3 up here. So I'm going to leave this here for a second, and I'm going to actually start by rewriting this integrand as the integral of 8x over 1 plus 4x squared plus 3 over 1 plus 4x squared. Notice they have the same denominator, so I would add across the numerator. I get the exact same integrand. But because now I have two terms being added, I can find each integral separately. So in other words, I can do each one of these as its own integral. Well, this first one is going to use this substitution that I started over here. So it works out perfectly. 8x dx was equal to du. So this becomes the integral of du over just u. And because this is just du over u, it does become natural log of the absolute value of u. And we can finish this out by substituting u back in. Natural log of the absolute value of 1 plus 4x squared. And now we can go ahead and find this indefinite integral. Now I have just a constant on the top, which is nice because I can think about just pulling it out to the front. So I have like a 1 over 1 plus 4x squared. which is now starting to look like this arctangent formula. But instead of having just a single variable squared, I have 4x squared. So I'm going to need to do a little bit of rewriting. I'm going to think about this as 3 times the integral of 1 over 1 plus 2x as a quantity squared dx. And I'm going to need to make a substitution to turn this into just one variable. So I'm going to go ahead and choose a different variable for the substitution. Since I already used u over here, I'll do a k substitution. So k is equal to 2x, dk is equal to 2dx. Well, I just have a dx that I want to replace, so I'll divide by a half, or multiply both sides by half, divide by 2. So I get 1/2 dk equals dx. So I'm going to replace this dx right here with 1/2 dk. So this dx will become a dk. So I have a 3 in front. The integral, this dx will become a dk, and the 1/2 I'm going to choose to put in front with the 3. So 3 times 1/2. And now this part is 1 over 1 plus k squared, which is just perfectly arctangent k. The value of a is 1 squared. So I have just a is equal to 1. This a squared is 1 squared. So my answer ends up being 3 over 2 arctan of just k, because it would be k over 1, which is just k, plus c. And then I have to remember to substitute 2x back into k. So my final answer is natural log of the absolute value of 1 plus 4x squared plus 3 over 2 arctan of 2x plus c. In this last example, I have the integral of x all over x squared plus 4x plus 13 dx. Now here, it definitely doesn't look like one of these general antiderivatives, because I don't see just those two pieces. I see a trinomial here, and I don't just see any of these denominators over here. So if I were to think, let's try u-substitution first. I will show it, and then I'm going to erase it because it's incorrect. I would try maybe u equals x squared plus 4x plus 13, the entire denominator, and I'd get du equals 2x plus 4. So I don't have that in the numerator, so that's no form of this is going to work out. So I'm going to go ahead and erase it. And on this one, the strategy is using an algebraic technique called completing the square in the denominator, because the denominator also doesn't factor. So when I see a trinomial, one of the things I might also try is to factor it, but here I have this prime number 13, so I'm not going to have this work out as something that's factorable. So I'm going to use this algebraic technique called completing the square. So let's go ahead and go over and review that process. So I have x on top. I'm going to leave the dx. So completing the square has to be on the terms involving x, and I want a leading coefficient of 1, which I have, which is great. So I'm going to have x squared plus 4x. So I'm going to leave those terms on the left, and this plus 13, I'm just going to move it all the way over to the right hand side. I'm going to basically ignore it for a minute, because I want to complete the square on the two terms involving x. Now, the formula for completing the square, I'm going to write it up here for our reference. So if I have x squared plus bx, so I'm going to make it generic, the value that completes the square is taking the value of b, so we're going to have plus b over 2 as a quantity squared. This is the number that completes the square. And when we say completes the square, what we mean is that this is now going to factor, so this whole quantity here will now factor to x plus b over 2 squared. That's now how this trinomial will factor. So this is an algebraic formula. Let's go ahead and implement it and see how it works. So the value of b right here is 4. The value of b is positive 4. So to complete the square, I would have to divide this by 2. Well, 4 divided by 2 is 2. And then square that number. Well, 2 squared is 4. So I'm going to add the number 4 to this quantity. That's what's going to complete the square. So now these three terms, this trinomial that I've created, is going to factor very nicely. So it's going to factor 2. So I'm going to have so far the integral, I'm going to have an x on top. Now these three terms are going to factor to x plus 2 squared. So whatever the middle term cut in half was, so positive 4 divided by 2 was 2, that's what ends up being the value here, just b over 2. So this right here is x plus 2 squared, and you can check by multiplying it out. X plus 2 becomes this trinomial. And that's great, but we just changed the problem. We can't just up and add 4 to the denominator. That's just completely changing things. But if I add 4 and at the same time subtract 4, now I have just cleverly added 0. So positive 4 and negative 4 added together are just 0. But I'm going to choose to group the positive 4 with the first two terms and then add negative 4 plus 13 together to give me a plus 9. To give me a plus 9 dx. So now I'm starting to get something that looks a lot like this denominator here, something squared plus something squared. So I have, it's reversed, so the constant a is right here, a squared, so this would be 3 squared, and it doesn't quite look like a single variable yet, but it will after we do a substitution. So the next step is doing a substitution. I'm going to let u equal x plus 2. Then du is equal to dx. So let's go ahead and replace what we can so far. So I have the integral, I have this x plus 2 right here was equal to u, so I have u squared plus 9. I'm going to rewrite 9 right now as 3 squared. And then here, dx was equal to du. The problem is that I still would have an x on the top, and I don't want x's and u's in the same integrand. So I need to somehow, if possible, get rid of this x. And that's where the original u equals x plus 2 substitution comes in. So I can go ahead and solve this equation for x to write it in terms of u if I subtract the 2 to the other side. So u minus 2 is equal to x. So I'm going to take u minus 2 and let it be the numerator. So I have u minus 2 on the top, and then u squared plus 3 squared in the denominator. So here, now we end up with something that looks a lot like the last problem that we just solved. I'm going to go ahead and solve it like the last problem, which means to split this up into two integrals. So the integrals, I'm going to move my work up here since I'm running out of space. This is the integral of u over u squared plus 9 du minus the integral of 2 over u squared plus 3 squared du. Now I'm choosing to keep this right-hand one as u squared plus 3 squared because this is the one that's going to turn into an arctangent. It has just a constant on the top. But over here, since I have a variable on the top, this one's going to be a u-substitution, or I'm definitely going to have to use a different variable because I've already done a u-substitution, but it's going to be a substitution here. So I'm going to go ahead and let k equal the denominator. So I'm going to have k is equal to u squared plus 9, then dk is 2u du or 1/2 dk is equal to u du. So this first integral is going to be equal to 1/2 the integral of dk over k. Well, since it's just k on the bottom, I can find the antiderivative as natural log of the absolute value of k. And substituting u back in, I have 1/2 natural log of the absolute value of u squared plus 9. But u was x plus 2, and our original problem was in terms of x. So we're going to go all the way to 1/2 natural log of the absolute value of x plus 2 squared plus 9. So that's this first part here. And then we're going to have minus 2, and then I'm going to think about this as 1 over u squared plus 3 squared du. And this is an arctangent. And arctangent does have that 1 over a in front, so the value of a being 3. So I'm going to have negative 2 over 3 arctangent of u over 3 plus c. And then we'll go ahead and plug our u back in, and our u was way over here, that was x plus 2. So we have minus 2/3 arctangent of x plus 2 over 3 plus c. So that same thing I'm just going to write down here again, as now my answer is all in terms of the variable x. And here we could multiply all of this out, and you'll notice that it's the same thing as the original denominator, x plus 2 squared plus 9. Look, that is just the original denominator over here. So we can have 1/2 natural log of the x squared plus 4x plus 13 we started with, minus 2 over 3 arctangent of x plus 2 over 3 plus c as our final answer. This problem obviously took a lot of work, and there were a lot of steps. We had an algebraic component of completing the square, a u-substitution, then we had to split it up into those two separate pieces. So we had to do this part here, and then we had to do this part here and split it up into those two separate integrals as we did in the previous problem. One was solved with a substitution, the other with a transcendental integral. The last thing that I will mention, not necessarily about this problem, but about transcendental integrals, is that the value of a doesn't have to be an integer. So we've been looking at sort of these nice quantities of perfect squares. So 9 is a perfect square. I can rewrite 9 as 3 squared. But I just want to take a second to remind you that I can also have any number be rewritten as a perfect square. So if I had just the number 10, that's the same as the square root of 10 squared. So although if I see perfect squares, it's a nice indicator that it could be an arctangent or arcsine, a transcendental function, but if I don't see those perfect squares, it doesn't mean that I cannot create a perfect square by using a square root.